Okay, in this lecture, we're going to go over the last section in Chapter 17. It's going to be Section 17.9. And we're going to be looking at charges on conductors. So if we're looking at a static configuration with no net motion of charge, that's a definition of static, no net motion, the electric field is always zero within a conductor. So the charge on a solid conductor is located entirely on its outer surface. If there is a cavity containing a charge, positive Q, within the conductor, the surface of the cavity has a total induced charge of minus Q. So in other words, you've got all of the charge here on the conductor on the outside. Now, let's say we put a cavity in here, and let's say we put a charge in here. When you put that charge in here, you're going to have an equivalent charge around here of minus Q, and that is, in other words, for the electric field to continue to remain zero across this Gaussian surface, the surface of the cavity must have a charge of minus Q in order to balance it. That way you have no net electric field. Now, when you do that, since obviously this is not included in the conductor itself, it's in the cavity, and you create a minus Q around here, your surface charge is going to have to help compensate for that in order to keep the charge the same. So the surface charge ends up increasing by an amount Q. So it may sound a little confusing here, but this is just the theory of electrostatics and charges on conductors. So we're going to start out here. We're going to have a conductor, and it's going to have a solid charge Q prime, and that's going to be distributed over the surface of the conductor, and the situation is considered to be electrostatic. So there is no electric field here within the conductor, nothing within the conductor. So because that electric field is considered to be zero at all points within the conductor, the electric field at all points on the Gaussian surface must be zero. Now, this Gaussian surface can be in several different spots, and expanded here, there, wherever. But let's say now, to complicate matters, that we have a cavity here. In order for the electric field to continue to be zero at all points on the Gaussian surface, the surface of the cavity here with a charge of Q in it, this surface must have a total charge of minus Q in order to keep things balanced. And once you have that particular situation where you have a development of minus Q here, you've got to keep the charge all the same. So the outside here, in order to counterbalance that, to keep the entire charge Q for the conductor constant, you have to add another positive Q out here. So that's a lot of the description here. Now, here's some interesting stuff, electrostatic shielding. So suppose that we have a highly sensitive electronic instrument that we want to protect. I mean, or it could be anything else, from stray electric fields that might give erroneous measurements. We're going to surround the instrument with a conducting box, or we line the walls, floor, and ceiling of the room with a conductor, such as copper. The external electric field redistributes the free electrons in the conductor, leaving a net positive charge on the outer surface in some regions and a net negative charge in others. So if we take a look here, we've got our instruments inside here. We put it inside a conducting box. So the total electric field inside the box is going to be zero, but we're going to have some charge over here and some charge over here, since we're trying to protect it, and it's in an external electric field. That external electric field is going to have negative charge build up over here on this side, positive charge build up on that side. So this charge distribution causes an additional electric field such that the total field at every point inside the box is going to be zero. The charge distribution on the box also alters the shape of the field lines near the box, which you can kind of see here. And such a setup is often called a Faraday cage. So your microwave oven is in fact a Faraday cage in reverse. The metal grid on the door, window, and the metallic walls on the interior are designed to keep the electromagnetic radiation that heats your food from escaping you. So the effect of putting a conducting box in a uniform electric field is what you're seeing here. The conducting cage keeps the operator of this particular exhibit perfectly safe, which I got to admit is, it's neat. A little unnerving, to be honest with you, but that's what you're looking for here. So detectives use a forensic Faraday bag, such as this one, to isolate a confiscated cell phone from the cellular network. The bag has a conductive coating that blocks the electric field component on a cell phone signal.